It's always important for people to appreciate that what I just showed you in terms of describing starting amounts of material and this thing called K is that no matter how much I say it, I haven't said it enough. That you have to get out of your brain this idea that there's the stuff you start with, it reacts, it goes to completion, there's your end result. What's actually going on is that we are starting with arbitrary amounts of all of the material in the chemical reaction. In this top example, I am starting with all water and no oxygen and no hydrogen, and I'm saying ready, set, go. And when I say ready, set, go, you're seeing this reaction fall down from the right side to the bottom to the left, and it makes the following sort of result: 2 hydrogens, an oxygen, and 98 waters. That's what happened. All right. Well, let's start all over again, and let's do some entirely new combination of stuff in the container. This time in my container, I'm going to put 60 hydrogens, 30 oxygens, and 40 waters. And I'm going to say, ready, set, go. And I'm going to let that reaction happen. And that reaction will happen, and when it's all said and done, I will be at equilibrium. And what will the equilibrium be? You got it. 2 hydrogens, 1 oxygen, 98 waters. In other words, it doesn't matter what my initial concentrations are. No matter what they are to start, there is that thing they are when they are over. They are the final amounts that you see shown here. So the question becomes, what is that final amount? What is that K value? Well, it's an easy value to calculate when I'm able to make ratios like what we talked about here, where I ended up having 98 waters, 1 oxygen, and 2 hydrogen. Those together, ratioed to make this value, I can find in the back of the book. This value right here, found in the back of the book, which is temperature dependent, is the equilibrium constant for that exploding hydrogen balloon. Now, that value is something we will spend the rest of the semester trying to find, trying to identify. Over and over again, I'm going to show you a chemical reaction. Maybe it's an acid-base reaction. Maybe it's a solubility reaction. Maybe it's some sort of gas reaction in the atmosphere. And I'm going to say, give me your stuff, put it in a bucket, go! And we're going to wait. And it may happen fast, or it may happen slow, but when it's happened, it's going to get to K. I'm going to fall down the free energy hill from one side or the other, and there is K at delta G equal to 0. One of the things that's interesting about this is that I now have a new way to talk about whether a reaction has happened or not. We learned from thermodynamics that delta G is negative when a reaction happened, and we learned that delta G is positive when a reaction happened. Well, what can we say about K and whether a reaction has happened or not? Well, it makes sense that if I end up having K greater than 1, a reaction happened. If K is less than 1, then I say a reaction didn't happen. And before you go getting all confused and wondering how that can be, just look at this. If I ratio A and B to get K, doesn't it make sense that if I end up having more stuff form B than A, then B over A is going to be greater than 1, and I can say that the reaction moved to the right, that it happened as written. On the other hand, if after I put the stuff in the pot, A and B, and I say go, and I end up making more A than B, then my number in the denominator is going to be bigger than in the numerator, and K is going to be less than 1. The reaction didn't happen, or the reverse reaction happened. So, rule of thumb, if a reaction happens as written, in other words, if it happens going to the right, it's going to produce a K value at equilibrium equal to a value greater than 1, and that's going to mean that delta G was negative. Conversely, if a reaction doesn't happen as written, it means that the reverse reaction is written. I make more stuff that's on the left side, more stuff that's in the denominator, and therefore K is less than 1, and delta G is positive. The reaction did not happen. we will learn that there is actually a very nice, simple relationship between delta G and the equilibrium constant K in an upcoming lecture. But there's the actual number describing it. Delta G is equal to minus RT log K, my equilibrium constant in delta G. And that negative sign right there is what it is that flips things so that a negative delta G corresponds to K being greater than 1, or a positive delta G corresponding to K being less than 1. But we'll look at this numerical sort of result coming up in the future.